All right, so I'll go through, I guess, more of the introductory part of this, and then after that, I'll start showing a bit more about how you can actually make a cryptocurrency in Python. Okay, let's get set up. So before we talk too much about cryptocurrency, first of all, my name is Samuel. I'm an engineering manager here at SurveyMonkey. And I've been interested in cryptocurrencies for a while now. But really, before we talk about that, we should talk about what is money anyways. So money is a really fascinating concept in and of itself. I don't really understand it. It's like, what is this thing that I can exchange and somebody gives me, you know, like a coffee in return? So money it's kind of a fiction. It's more of like a story that we tell ourselves, even though its value ultimately comes from the banks and the institutions and governments that back it. Really, it's, you know, the money has value because you think that it has value, and I think that it has value, so it allows us to make that exchange. So economists have a pretty standard definition of what money is, and so the main one is that it's a medium of exchange, so it allows people to exchange goods and services. It's a unit of accounting, so it's also what we denominate you know, debts and credits and prices in. And it's also a store of value, hopefully. So hopefully, if you get $1 today, you don't have to spend it right away. You can wait until, you know, next week to buy that coffee. So with computers and with the internet, we also have digital currencies. So these are currencies which are not real, but they're virtual. So a lot of games, if you played Diablo or Pokemon, who's played Pokemon Go? Is it, yeah, okay. So if you played Pokemon Go or Clash of Clans, I think that is, or a lot of other games, you've used virtual currencies. So the difference here is that instead of being controlled by a central bank or a government, they're controlled by a private institution. So does it satisfy those three properties that money had? Is it a reliable source of value? Well, maybe not necessarily. If you're like me and you were cheating in Pokemon Go and you got your account banned, you lose all your coins. The company can just ban you, and you're out of your whatever you bought. So just one aside, which is that in virtual currencies, normally what you'll see is that it's divorced from the actual the idea that you have in your mind about money. So when you're buying a Pokeball in Pokemon Go, you're not spending Canadian dollar, you're spending these in-game coins. And the reason for that is because it's an emotional decision to buy something, and when you're thinking about what the value of that dollar is, you're less likely to purchase. So that's why instead a lot of games you buy gems, for example, and then you spend those gems in the currency, in the game. So instead of having a currency which is centrally controlled by this institution, there's a concept called cryptocurrencies. So that's my definition of that is a digital currency that's actually secured not by a private company, but via cryptography. So the best known of these is Bitcoin. Most of you have probably heard of that if you're here. And Bitcoin came about, it was actually built on a bunch of previous ideas that had been around. But the reason that Bitcoin kind of became more successful is it was the first time that there was a real implementation of a cryptocurrency. So that was released on a forum in 2009, and then people started you know, running that. And then since then, there's been a lot of new cryptocurrencies that have come out, some like Ethereum or Litecoin, a couple others, a lot of them actually now that are starting to be created. And a cryptocurrency gives you a couple of nice properties over just regular digital currency. And one is that it has decentralized control and decentralized kind of issuance. So rather than having these coins which are issued by a company, you have the way that those are issued is known and it's public, and anybody can participate in this network, and everybody in the system kind of contributes to the control of the system. And sorry, let me get my mouse here. And the other part of that is that these cryptocurrencies are normally, there's financial incentives for participants to secure the network. So it's not a goodwill that people are participating in this. There's actually a reward system that incentivizes people to help participate. So I'll talk a bit about Bitcoin specifically, just because it's the best known and the kind of the most widely used. And I don't want to focus too much on price. So, like, this is not again, nothing I'm saying should be considered investment advice, but focusing on the price I think is useful a bit for just telling the story of where it's come from. So this is just the price of Bitcoin over the past 8 years or so. So here's that again in logarithmic scale instead. So it's a bit easier to see. In 2011, it reached parity with the US dollar. So that was around the time when it was starting to get, people were starting to be aware of it. So Bitcoin was created in 2009 by a programmer or a group of programmers under the pseudonym Satoshi Nakamoto. And it really initially caught on with like the crypto anarchist community and like the cypherpunk communities. So people who are really distrustful of the government will see something like this and they're like, oh, this is the new currency. This is going to be revolutionary. This is the new society. So in 2010, the story is like somebody on the forum, the Bitcoin Talk forums, paid 10,000 Bitcoins for a pizza. For 2 pizzas and got them delivered to his door. So that was a big milestone because it was the first time that people had actually exchanged this for like real goods. So Bitcoins are essentially created via this process called mining. And for Bitcoin specifically, the schedule that they're issued in is well known. So it's deflationary. Anybody who mines Bitcoins is aware of this, meaning that there's a fixed number of Bitcoins that would ever be created. And the number that's getting issued over time is slowing down. So there's about 17 million that have been created to date, and the total cap for that is 21 million. And of that 17 million, actually, the estimates are that about 30% of the coins that have already been created have actually been lost or are destroyed. So that's kind of an interesting approach. It's not something where you can suddenly decide, a central bank can't decide to say, oh, we're going to raise the inflation rate, or we're going to change the rate. So instead, it's actually built into the code that is slowing down over time, and that is going to hit that cap. So the core innovation in Bitcoin and in these cryptocurrencies, in my point of view, is this technology called the blockchain. So that's, if you've heard about that, that's the technology that underlies Bitcoin and a lot of other cryptocurrencies. And what the blockchain does is it's a solution to the problem of distributed consensus in a network that may have malicious nodes. So if you control all of the nodes in a network, if you're running the code on all of these computers, there's other consensus. So consensus, I should explain, means having all of these nodes in this network agree on the state of something. So agreeing, for example, how much or how many Bitcoins I have, or how many Bitcoins somebody else has. We want all of these nodes to agree so that anybody can join this network, participate, and also track that same state. So if everybody was, honest and cooperative, then you wouldn't need to have a blockchain really, because then you can just use a standard consensus algorithm like Raft or Paxos, if you've heard of those. But blockchain was really the innovation that lets you arrive at consensus even in the presence of a minority of nodes that are possibly malicious. So even if you don't trust anybody in the network, but you trust that a majority of the people are honest in this network, then you can still reach this consensus. So the way that works is each node in this network maintains a copy of this ledger, which basically records all of the transactions since the beginning of the cryptocurrency. So since 2009, you can see all of the transactions that have happened in Bitcoin. And when you want to make a transaction, so let's say this node decides that they want to send they want to make a new transaction, that node then decides to broadcast it to its peers. And then the ones that are honest, again, or that are cooperative, will then forward those on to their peers, and so on until the entire network is aware of that transaction. So now everybody in the network knows that this transaction is supposed to happen. And this transaction is still unconfirmed, so it hasn't actually happened yet. And the way that it's going to become confirmed is that we're going to include it in something called a block. So this block is going to include all of the transactions that are happening in a certain period of time. And each node is trying to find the next block that's going to be added onto this list. So that's what the blockchain term refers to. It's this chain of blocks. And when you find this next block, you actually get the reward that the block gives you, so a certain number of Bitcoin. And then you also get the transaction fees of the transactions that you're deciding to include. So that's the incentive. So I could be running this and not including anybody's transactions, and then Bitcoin wouldn't work. But hopefully the majority of the nodes are deciding to include these transactions, and so that's how the system, yeah.
Just to clarify that a little bit more, so you got the bit where you say, I want to do a transaction, let everybody know on the network, and everybody informs everybody.
Yeah.
And then there's the block. You start the block. Get the connections.
The transactions in the box. So yeah, so the question is, how do the transactions relate to the box? So the transaction first gets broadcast, and that's held in this pool of unconfirmed transactions. So each node participating in the network has this list of transactions that they get to confirm. And each node at the same time is trying to solve this puzzle, that's called the proof of work puzzle. They're trying to find something which makes the next block valid, and they're going to include the transactions that they know about. So this node might be looking for the next block, and it knows about a certain set of transactions. And so when it finds that block, it's going to include those transactions in it, and then it's going to follow the same process of broadcasting that block to the rest of the network. Okay. So because communication, so the process of mining is finding this next block. So that's what people call mining. You're solving that puzzle. And on average in Bitcoin, it takes 10 minutes for the network as a whole to find a block. So, and that difficulty gets adjusted over time, so that on average it's still every 10 minutes you're finding a new block. And the communication isn't, the network is unreliable. The communication between these nodes is not instant, and a lot of these could fail. So each node could have a different view of the transactions, right? Like if I'm broadcasting one, it might not get propagated to the right. Yes. Yeah, so I'll get to that, but yes, it'll take at least 10 minutes. Yeah, one more, and then. Yeah, so then that you've been basically, you can't make any transactions if depending on how malicious they are or what they're doing. If they're trying to censor you, then you won't be able to make those, which is why you normally try to connect to a diverse set. Yeah, and a lot of P2P networks have that same kind of issue.
So where the 21 million blocks have been found, there will be more transactions in the network.
So it's like a decay. It's on a halving schedule. I think I'm not sure exactly of the time frame. Every 2 years maybe, but so there's always a reward, but that reward just keeps decreasing. Okay. So yes, to your question, it does mean that a transaction takes 10 minutes basically to get confirmed on average. But not only that, the more confirmation, the more blocks that have been found after your transaction was confirmed, the harder it is for it to be changed. So if it's only in one block, somebody else, so that could happen here, right? This person could find a block, and then at the same time, this person could find a block with different transactions in it. So at that point, these two chains are now conflicting, and you're not sure which one is valid. So the rule that nodes follow is that the longest chain is the one that is correct. So that's, and what that means is that even if there's two blocks that are conflicting, the network would start adding more and more blocks on top of that every 10 minutes. And then once you have a certain number of blocks, it becomes even harder to change the ones that happened before. So most of the time what they say is to wait for 6 confirmations before actually considering a transaction to be valid. So yeah, an hour for Bitcoin. The length of the chain is every 10 minutes, one block gets added. So I think Bitcoin is now at 3 million, something like that. Yeah, somebody's downstairs, I think, and calling me. So somebody wants to let them in. So yeah, I should talk a little bit about what a fork is before kind of talking about the applications for this. So yeah.
The transactions involve entities. Who manages that?
Yeah, I'll kind of show that, and the second part I'll show like a toy cryptocurrency from scratch built in Python, so that might explain that a little bit more. So yeah, a fork. Did anybody hear about the Bitcoin Cash split that happened? Yeah. Yeah. So yeah, on August 1st, actually a bit after that, the Bitcoin forked into 2 different currencies. And what happened was, so here's what the blockchain looks like in an abstract. Each block has the one before it. And then at a certain point, that block might fork into 2. So A here might be a node that was mining on this block, and B as well. and they might find 2 blocks. And in a normal scenario, this could actually happen in a lot of different ways. So one possibility is that maybe A is cut off from the rest of the internet, and it can't actually communicate with anybody else. So that's a fork that happens, and it happens, it will happen. And so while the network is partitioned, there is a period of time where these chains are proceeding in parallel. But hopefully once the network rejoins, or once this node rejoins, because of that rule of the longest chain always being the correct one, then A, if it's honest, would then notice, oh, okay, this is a longer chain. I'm going to start using this one instead. And so then that fork gets resolved by itself. Yeah, so if there were transactions in here, A would then notice that, oh, this new chain doesn't have them. I'm going to try to now include them in the next block that I mine on top of here, if they weren't already in that chain as well. So that's one case that a fork could happen. Another one is maybe A or B and C are malicious. Maybe they're actually withholding that information. So maybe A found a block, but it's keeping it to itself. And the reason somebody might want to do that is that if I keep this to myself and then I find the next one, then once I find the next one, I can broadcast it, and then I have a bit more, I have a chance of having, mined those 2 rather than just the one. So that's another case where in the presence of malicious nodes, you can have a fork. Yeah.
In case we have fork and a subsequent merge, timing of all the transactions, does that change your?
So there is no merging really, because there could be conflicting. Yeah. So if anybody's used Git, actually this is a very similar. It's very similar to Git, except that you can't merge. So you always have a merge conflict. So because there's no merging, you don't have to really worry about the ordering. Yeah.
Well, the timing of those transactions will stay right?
Oh yeah, they will. And then the last case that you can have a fork is the one that we saw with Bitcoin and Bitcoin Cash, and that's where A, let's say, has a different view about what it makes a valid block than B and C. So this was a big source of debate in the Bitcoin community was how many transactions should we allow into a block? There has to be some limit. We can't just have unlimited number. So Bitcoin originally was considering that each block should have at most a megabyte of transaction data. And anything with more than that, we're going to reject it. That's not a valid block. We're ignoring it. So on one side of the debate, there was miners, so people who are running these huge rigs to find Bitcoins, basically. And they get rewards for including transactions. So the more transactions they include, the more rewards you get. And also transactions can happen faster. Because right now, if there's only 1 megabyte every 10 minutes of transactions, then the network is limited to a couple per minute even.
How big is one transaction after that megabyte?
It might be a couple of kilobytes. Yeah. So that was one side of the debate. People saying, oh, we should include more transactions. It'll let more transactions happen. But then on the other side was people who were saying, oh, we should keep this true to the original vision of what Bitcoin was. We should keep it at 1 megabyte. Bitcoin should really just be like a settlement layer. So Bitcoin you can use for like larger transactions, maybe for settling larger debts or larger purchases and things like that. But really, if you want to do Bitcoin shouldn't be something that we use to pay for a coffee. If you want to do that, then we should build something on top of Bitcoin. So those were kind of the 2 camps, and the details behind that are really, really involved. Yeah. So I won't talk too much about that, but come find me after if you're interested. I don't really understand it that well either. But
last question,
yeah.
Since you moved off course, so since the block only happens every 10 minutes-ish.
Yep.
Longest block wins. Seems likely that they'll be tied all the time.
Yeah.
What's the tiebreaker?
The tiebreaker is when you find the next one, and then that one becomes. So for that 10 minutes, there could be. Yeah. Okay. I'll talk a little bit about the applications, and then I'll jump into the demo portion. So Bitcoin by itself, people are using it as kind of and that's not really a currency anymore, I would think. It's what I'm excited about is kind of the technology behind it and what other applications outside of just paying for coffee that this technology has. So one of the big ones is smart contracts. Has anybody heard about smart contracts? Yeah. So smart contracts are a way of taking a legal contract, and a legal contract will, have some financial, might have some like clauses that say that this transaction happens if this happens. So a smart contract is trying to take kind of the bulk of that, the part that can be automated and automating it, and then the part that still needs a human input, for example, like deciding, oh, did this event happen, or did this person like default, or something like that. The parts that need human input are discretized, and then those can be used to kind of trigger these conditions automatically. And so these have a lot of other applications, things like automatic market makers. So a contract which automatically provides liquidity in a market, for example. There's a lot of other ones. Automatic escrow, for example. So having a trusted party which determines when the escrow conditions have been met, and then doing the disbursement automatically for that. So there's a lot of stuff being done with this. So Ethereum is a cryptocurrency, probably the best known, which has an implementation of this. So as part of its blockchain, it has a fully Turing-complete language, which you can program. And there's a language which is actually very similar to Python, which compiles to that virtual machine. So that's a whole another, I think that would be a whole nother talk. Another one is decentralized storage. So if any of you watch Silicon Valley, the internet, which is stored on everybody's phones. So there's something called IPFS, which is where you can kind of rent out your storage. There's a couple other projects which are doing this. And what the blockchain would do is that it creates that immutability. So because blocks get added and it becomes harder and harder to change the past, you can have this kind of storage where things are immutable. And then the other ones, the big ones are finance. So there's some consortiums which are trying to apply this technology to like private, so not just a public network where anybody can join, but really like a private network between a couple of banks, for example, and to use that as a settlement layer. So that's another application which I think actually has a lot of potential, because I think that's probably the best case, one of the best use cases for this. And the last one I'll mention is energy markets. So if you have a solar panel on your roof and you want to sell your additional power, if you have to go through a central market, if there's something wrong with the network, then that's not really a great thing. So if it can be peer-to-peer and decentralized, so that I can sell it to my neighbor without having to go to a central kind of marketplace, that's another possible application. Any questions on that so far? Okay, I have maybe 10, 15 more minutes. I'll show the demo now. So let's go to this. Yes? Yeah, so I didn't talk about that. So so the assumption is that a majority of people are honest, because if there's a majority that's dishonest, that's colluding, then they can control the network. Because what happens is, if they control a majority of the mining power, if they have enough CPU power to solve this puzzle faster than everyone else, then they can kind of front run that chain, and they can always have the longest chain. So they can always find the next block on the longest chain, or if not always, then probabilistically enough times that they can always have the longest chain.
Is there a protocol within the blockchain to prevent the theoretical dishonesty?
So within Bitcoin, there is not. And actually, that's one of the problems right now with Bitcoin, is that it has become kind of centralized. So the original vision of it is that it's completely decentralized, but because of how economics works, it tends to, it tends to become more cost-effective to centralize how you're doing this mining. So you'll have large operations. I think now, most of the mining power is controlled by 5 or 6 companies or organizations. So that's kind of a problem that's plaguing Bitcoin, at least. Some of the other ones have different hashing algorithms or different proof of work functions, which make it more difficult to do that. But still, that is a kind of a limitation, something to be aware of. Okay, so this is something that I built just to show you how a cryptocurrency is built, or how you would build one. Is this big enough for everyone? Can everybody see? Okay. So there's a couple of concepts to know before we talk about that. So the first is the hash. Does everybody know what a hash is, or do I have to? Yeah? Okay, I think most people know. So I'll just show you that in Bitcoin, in Bitcoin. Can I zoom in? Yeah. Yeah, so in Bitcoin, the hash function that's used is SHA-256. So with SHA-256, it's a 32-byte hash. And the point is that changing a single letter or changing the input just a little bit will change the output. And it's not, it looks like a random number even though it's not, because if I rerun this again, it'll be the same. So what the property that Bitcoin uses is that you'll notice that if I take the hash, the SHA-256 hash of this string, it actually starts with these 3 zeros. And so that's a property that, that's what we want in this, in Bitcoin, is we're finding the hash which starts with this, a certain number of zeros. And because a hash, you can't invert it, given a hash, you can't find the input. The only way to find this is to actually try a bunch of different inputs until you find one that matches. There's no shortcut to figuring out what this should be. So that's a hash. And then the second kind of underlying concept is public key cryptography, also known as asymmetric crypto. So this is what powers technologies like SSL, secure sockets, or TLS, I guess. And the main things that you can do, so the idea is that you create a pair of keys. So you have a private key, and then you have an associated public key. And there's a couple of things you can do with it. The first is encryption. So I can encrypt using the public key. So anybody can encrypt a message for me with this public key, and then only me or somebody who holds the associated private key can actually see what was encrypted. So the analogy for that is, think about I have a key in a padlock, and I can give any of you a copy of this lock, and you can put something in a box and lock it. And then only me, as somebody who has that key, can actually see what you put in that box. So that's one operation that these support. And then the second one that we'll see here is signing. So in signing, if I have a private key, I can create this unforgeable signature for the data that proves that the data hasn't been tampered with and that I actually signed it. And then anybody who has the associated public key can then verify that signature is valid. Okay. So the way that you do this in Python, and this is using a library called Cryptography, it's pretty well supported. So here's, you create a private key. So you're generating a key pair, and this is the curve that Bitcoin uses in its cryptography. So there's a couple different methods, but this is elliptic curves, which is a pretty secure one. So yeah, so the private key, and then you have an associated public key. And then when you have a data, which is just any set of bytes, you can take the private key, and then you sign that data using some signature algorithm. And then that signature is now this other byte string, which represents that, okay, this data hasn't been tampered with, and I did sign this. And so now if somebody has my public key, they can, using my public key, verify that the signature is valid. So if I try to verify this with the original data, this won't throw an exception because it means that that was valid. If I pass this some data which I'm trying to say was signed, then I get an invalid signature. So that's public key cryptography. Merkle Trees, I won't talk too much about this. They're a really cool data structure, which you should look into. But the way to think about it is just it's a list of items, and then there's a hash of all of those items within it. So you can't make a change to any of the items in this list without affecting the Merkle root, the hash of all those items. And it has some nice additional properties with complexity, and it's used in Bitcoin and a couple others cryptocurrencies. So let's talk about addresses. So you're asking, I think, what is this address like, and how do you spend it? So an address in this currency we're going to make is the hash of a public key, and then only the person with the private key associated there can spend the public one. They can spend those funds. So here's how we're going to do that. We have this class, and then if we're going to generate this key pair of private and public keys, and then the address itself is the hash of it. So when I have an address, this is basically just this hash, but it also has an associated private key and a public key, and then those are what I can use to spend those funds in that address. But to send it to an address, you use this public value. So that's an address. Couple more pieces to talk about. So then there's, on top of that, we're going to build a transaction. So a transaction is a sender, the person who's sending it, the person who's receiving it. Both of those are addresses. And then the amount you want to transfer. We'll just use an integer for this. And then we also have a nonce, which is basically just a counter of how many transactions have been made from that account, and that's to prevent somebody from replaying a transaction. We're going to sign this transaction using the private key of the sender. So this ensures that only the person who has that private key can actually do the sending. So here's the model. I have to zoom out a little bit to show you all of this. This is my first time doing a presentation with Jupyter notebooks. It's pretty cool. So here's our model. Here's a transaction. So again, we have a sender and a recipient. Those are the addresses. The nonce and the amount. The amount is just the integer, and nonce is the count. And then the signature, which is going to represent that signed data. So a transaction has two operations it can do. The first thing is we can sign it. And so to sign it, we'll pass in a private key. We'll serialize all of the values. So basically these four things here, sender, recipient, nonce, and amount, we'll serialize those. And then we'll just sign it with a private key. And then the reverse of that is verifying. So to verify it, we do that same serialization of the data. And we'll do a small trick here because, and Bitcoin does this too, this saves some data on the wire, but basically we can recover the public key from the signature rather than storing the public key alongside it. So we can recover that key, and then we have a check here that says, okay, let's make sure that the key that signed it is actually the sender, the person that's trying to send those funds. So that just checks that those match. And then finally, we take that public key that we've recovered and we verify that the signature and the data match. And that's it for the transaction. So those are the two things. I can sign it and I can verify it. Good so far? Everyone with me? Yeah? This is kind of dense, I guess, but I find it really cool. So yeah, the last piece of this ledger. So what we're doing right now is we're building a ledger. Right now it's just going to be centralized. And so the final part that we have is the state. So the state is the global state of the accounts and the balance of each one. And so each node in that network actually has a copy of this entire state, basically how much each address has. And then we define this transition function, which applies a transaction and then returns you a new state. So a transaction is really something that modifies the state. It's a transition. So how does that look? So first we have a class, which is this account. So each account has a balance, starts at 0, or we can start it at more. We can start it at anything. And then we have a nonce, which is just a counter of how many transactions have started, have been made from this account. And then we have the bulk of the ledger implementation. So this is the state itself. This we're inheriting from a default dictionary. So a default dictionary in Python, if you haven't used it, it's a dictionary that you can, if you try to get a key that doesn't exist, it'll create you a default value. So this makes things a lot simpler. It means that I can just grab an account from the state, and if it doesn't exist yet, it'll initialize it at 0. And so then here's that transition function I was talking about. So we take a state, and then what we want to do is we want to apply a transaction to it, and then we'll get a new state as a result. And to apply a transaction to the state, what we do is we get the accounts for the sender and the recipient from the transaction. We're going to check that this signature is valid. We want to make sure that it's really the person who is sending actually did sign this transaction. And then we check that the nonce matches. So we're just checking that the account of the sender and the nonce in the transaction are the same. And then we're going to check that the sender has enough funds to actually make this transaction. So if their balance is too low, then we'll error out. And once that's done, now we've checked everything. So we create a new state, just a copy of it, just to keep things immutable, gives things a bit nicer property. And then we'll increase the nonce of the sender, and then we'll do the transfer. So we deduct from the sender, and then we credit to the recipient. And then we just return that new state. So this is the implementation of the ledger. So what I've just shown you so far, this is actually a working cryptocurrency. Like it's not decentralized, but it does keep track of balances, and it allows you to do transactions. So if what we wanted to do was have a centralized server which does these transactions, this is what we would basically want. And if you wanted to do it where you actually control all of the nodes, if you want it distributed but not necessarily decentralized, and you control all of the code, then you can use just a simple consensus algorithm that doesn't take loads and loads of energy to run. But let's see how the blockchain fits into this. So the blockchain is really that algorithm which lets you reach a consensus on what the state is of the system. So the first part of that is a block. So there's only two parts, and the first one is that concept of the block. So a block points to the previous one in the chain. It also has a nonce, and this is what we're going to use to try to find the valid block. So this is what we're going to kind of keep bumping, and we're going to check, is this valid? And then until it's valid, this is what we're changing. And then we'll have a beneficiary. So this is the person who's going to get the reward from mining this block. And then finally, we have these transactions, which are the Merkle tree I mentioned before. So transactions are just a list, and the list can't change unless the hash will change if any item in that list changes. So it kind of keeps that integrity. So the hash here takes all of the elements. So the previous hash, the nonce, the beneficiary, and the transactions list, and hashes all of those. And so to determine whether or not a block is valid, we'll just check that it starts with these two zeros. And finally, the last part of this block is to mine a block. So the way that we mine a block is we keep checking, is it valid? If not, we're going to bump up this nonce. And what that does is that causes the hash to change when you change the nonce, because it's included in this hash right here. So so just to show you how that works, here's a default block that I've created. No beneficiary, the nonce is 0, the previous hash is 0, no transactions. Here's the hash. As I change this value for the nonce, as I change this, the hash changes as well. And I'm going to have to keep trying this until I find a value which causes this hash to be 2 zeros, and I found it. So now this block is valid. I'm going to broadcast this to the network, this is ignoring kind of the whole P2P like network layer. This is kind of just the conceptual side of it. So you'd have to build that if you really wanted to make this currency. But that's how you find the valid block. And then finally, we have the blockchain itself. So the blockchain just has this mapping of blocks of the block's hash to the block itself. We keep track of the best one that we know about. So this is the longest chain that we know about now. And here's the next block. So this next block is the one we're currently trying to mine, and we're going to add it on to the end of our chain. And then the state just represents the current state of the ledger. So then there's basically only two things that you do here. So the first one is that to mine a block, what you do is, if that next one doesn't exist yet, we'll create it, pointing it to the previous one. We'll set a beneficiary if we want, and then we just mine it. And so that'll bump it until the block is valid. Once it's valid, now we set that as our new best block. And what we're going to do is we're going to change our state manually here. We're just going to credit the beneficiary of that block 100 coins, of our coins. And then the last part of that is the transaction. So what if I do want to make a transaction, I'm going to first apply that transaction to our state so that the state now reflects the result of applying that. And then I'll append it to the list of transactions in the next block that I'm mining. So, and then the way that this works, so I can show you now kind of an example of how that works. So I'll create 3 addresses, Alice, Bob, and Carol. And then I'll create a chain that starts as empty. And so this creates my 3 addresses, and each one has an associated private key. But right now, everybody's balance is 0, so there's no accounts yet. So the way that I would get one, so I can't make any transactions yet because nobody has these funds. So what I'll do is I'll first mine a block, and I'll make Alice the beneficiary of it. So once I do mine that block, we can see here's the first block that we found. So this is the first block. We're going to broadcast this to the network, and people are going to now start mining on top of this one because this is now the longest. So here, the nonce that it found was 180. It counted up to 180, and then it found that this hash here was valid, and there's no transactions in it, and the beneficiary here is Alice. And then now if we look at our state, we see that Alice has a balance of 100 because she mined that block. And so now we can create a transaction. So let's have Alice send Bob 25 of these coins. So we'll create the transaction. We make the nonce match the nonce of her account. And then we'll sign that transaction using her private key. And then we'll add that transaction onto our chain. And then we'll see what our state is after that. So now that I've made this transaction, you can see that the state has been updated. So now Alice has 75, her nonce has been incremented, and then Bob now has a balance of 25. And Bob could then, spend that 25 by creating a transaction, signing it with his private key, and then broadcasting that to the network. But this transaction isn't really confirmed until it's included in a block. So the way that would happen is you would mine this block, and for this we'll make the beneficiary Carol in this case. And so once this block gets mined, text is too small. Okay. So once this block is mined, so here's the block. It has a single transaction here, which got included. And then the hash here, notice, is valid again. And then the previous block was the one that we created in that first step. So now there's 2 blocks in our chain. The second block includes the transaction. And Carol was the one who got the reward for the second block. So here's the updated balances. Carol has the 100s, and Alice has the 75, and Bob has 25. So that's kind of how a blockchain works. That's about all I had for this presentation, but I can, actually, yeah, there's some further reading and some challenges that I can talk about, but I think we'll keep it at that. I think the pizza's here, so. Yeah. Yeah, so I think that's it. Yes.
So kind of what we asked earlier about as the incentive goes down over time, people become less interested with less networks, less node floating, harder to find. Given that finding a block is required to make a transaction happen, how is it not too expensive to do anything? Nobody's mining anymore. All your victims are worth nothing.
Right. Yeah. So in Bitcoin, there's a self-adjusting difficulty. So that hash that those ones I said, it's valid if it starts with 2 zeros. So the number, basically the number of zeros that it starts with, or like the number has to be below. That adjusts every 2 weeks, depending on how long it took to find the last n number of blocks. So every 2 weeks, Bitcoin will adjust that difficulty based on how long it took to find. So if it only found 10 blocks in, let's say, if it took like 2 months to find those 10 blocks, if suddenly everybody stopped mining and you're the only person mining, then for a couple of blocks, you'll actually find them very fast. Or sorry, no, you'll find them at the same slow speed, but then after a certain number of blocks have been mined, then that difficulty will adjust to match, so that on average, a block is found every 10 minutes.
So if there's a market crash and there's a plug in something and the client drops from $4,000 down to $100, everybody leaves the market.
Yep.
Still going to be possible because the difficulty will become simpler.
Right.
So
Right.
how is that? Is that like
So the difficulty, yeah, that's some code that's embedded in the Bitcoin code, which has that consensus. That's part of the consensus rules for Bitcoin. So yeah, whether or not a block is accepted as valid, you have to determine what's that cutoff for the difficulty. So right now, because everybody's running the same, similar versions of Bitcoin, they'll all have the same rules about what constitutes a valid block based on that adjustment. So I could create a fork of Bitcoin. I could say, okay, we're not going to have this difficulty anymore. It's going to change it. If I can convince enough people to use it, then that would become the new valid one. But yeah. Right. Right. Yeah, that's right.
So then you will get paid and you'll be happy to hear that.
Right.
You're getting paid just from the Bitcoin.
Right.
You're getting it at 100 from the Bitcoin, a million from the Bitcoin.
Right. Yep. 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 So the question is, what prevents somebody from making a chain that's longer just by padding it? So the reason that that isn't possible is because of that proof of work. So in order to actually find the next block, you have to do a certain amount of work that kind of proves that it took at least a certain amount of time to find it. So if I wanted to find, like, let's say 3 blocks, it's going to take me 3 times as long to do that. And in that time where I'm trying to do that, in that amount of time, somebody else is going to be trying to do that at the same time, and they're probably going to find the next one instead of me. Does that make sense, kind of? So the proof is because of that that hash function. It's not invertible, meaning that you can't just easily find some block which will make that hash valid. So you can't just like it takes a certain amount of time, and the expected number of tries that you'll have to do is, it follows what's called the Poisson process. So the first person to find that, it's basically like flipping a coin until you flip 10 heads in a row. And then once you've done that, then you show, okay, well, here's what I had to do that. And then each block that gets added then means that there was that certain amount of time before the previous block was known that it took to find this next one. And it could be, it could be a couple of seconds, it could be like an hour, but on average, it'll be that 10 minutes. And so this chain is progressing at a certain pace. And it's kind of like a race to see who can create the longest chain. And so to answer the question, which is, can you just pad it and create a bunch of new ones? Not really, unless you get super lucky. Yeah, so, yeah, okay, so yeah, I should also point out that the longest chain rule is not how many transactions have happened, but it's really just the number of blocks. So if I create a block that has 1,000 transactions and another block that has 1 transaction, these are now just actually the same length. They're just 1 block longer. Yeah.
So for getting malicious, if I finish my garage on the computer and solve it like that, and can every time get the longest chain. If I solve my broken system,
Yes. Yeah.
what stops me from just breaking it in? Where's the monitoring? Like, does the ledger say who does it? What okay, let's solve it.
There's a lot of all of that. So there are people who will be looking at what's happening, and you can't really divorce. So this is something that I think is worth mentioning, which is that kind of the idea of cryptocurrency was like to be completely separate from human politics and human so what happens in social situations. But really this it's a human endeavor. So there are people behind all of this. So yeah, so what are the checks for if you break the cryptography? So first of all, if you break the cryptography, we probably have other things to worry about. If you're able to to reverse a hash, so there's no known quantum algorithms which are able to reverse a hash either. Actually, that's not. Yeah, maybe that's not true. There might be.
But it's not true, right? So
Yeah.
But if I can solve it and I decide, there's the things you could worry about and there's me making up.
Yeah, and so that's where the second factor comes in, which is the crypto economics side of it, which is that you also have an incentive as a participant. If you're a holder of a cryptocurrency, you have an incentive not to make that currency devalue itself.
If I could cleverly punch part up and make that,
Yeah.
solve that, I'm gonna back on.
Yeah. Yeah.
So what I'm trying to figure out is what monitoring in place to see that? Like, if it logs, every single sheet I get, how do you know who's solving what? The ledger record that?
So the ledger does record it. And I mean, when you broadcast a block, normally you can see who broadcasts that block first. And people do monitor it. There's a website called, called blockchain.info, I think. Yeah, so this shows you kind of all of the blocks. So here's the last block that was found. This was found 7 minutes ago. And it's block number 481,000. And here's how many transactions were included in that block. And here's how many were sent and who relayed it. So who found that block.
Is that slower?
Uh,
See 1,000 transactions, try to calculate 1,000 blocks, right? One block per 1,000 transactions.
so no matter how many, so that's actually what's cool about the Merkle tree, which is that no matter how many blocks there are, no matter how many transactions there are in that in this block, it takes the same amount of time to find the next one. So whether a block is empty or if it has 1,000 transactions, that block, it's a constant time to calculate the hash of the block because that Merkle root is a single just hash. That'll change when you add a new transaction to it, but really there's only those 4 pieces of data or however many. So if I show you,
But you didn't have to get the transaction.
that takes some time, yeah.
Get the transaction.
Right. Yeah. So it depends on which cryptocurrency you're talking about. So and a lot of them, what it is just market determined. So anybody who is mining gets to determine what fees they want to accept and which ones they don't. Some of them have like a required minimum fee. And the reason that it's market determined is so that it can adjust to changes in price. So right now, if it was set at like 0.1 Bitcoin, then it would cost, $400 to make a transaction. That wouldn't be very viable. So yeah. So that's the cool thing about the consensus algorithm, which is also known as Nakamoto consensus, which is that you can do whatever you want. Like people participating in the network have the option of doing whatever they want. But yes, so an honest node does want to be mining on the latest block. The latest one that you know about, if you're honest, yeah. Yeah. Well, you don't really need to redo it. I mean, you'll reapply your transactions. So in the example I was showing with the code, what you would do is you would take all the transactions that you haven't confirmed yet. You would just reapply them on top of the block if they're valid. And then you switch your algorithm to, when it's mining, to just be doing that. Basically, you're just changing the hash of the previous block. You don't have to recalculate the entire history. And maybe one more question, and then I think the food is here. I didn't actually see it, or so. Oh, okay. Yeah. Yeah, so the hashes aren't really a memory address. They're just they're just a number that comes out of this hash function. So you're saying, so the question is if you're running some kind of code which is able to have like some vulnerability in it, or? Oh, so that is so each node in the network is running the code which has that verification check. So you could take the Bitcoin code and you could modify it. You could change it however you want, and you could run it and have it just not check even. Yeah. So if you try to submit a block, but then if everybody else is running the code which has that check, then your block won't be accepted. Even if you make a change, yeah, because it's sent over the network and they have a copy of it, they're going to be running it against their code. So as long as the code that you're running for that cryptocurrency is correct, which it's not always, and it's led to hacks and like people have lost their money in wallets. So that's something that is one of the big limitations, I think, is that it's very technically complex and prone to bugs. So you could, yeah. And so, well, I mean, it's not to create fake blockchains, it is to add to the blocks. Sorry? Oh, yeah. And so that would be a 51% attack. So that's if some government decided tomorrow, if the US government decides tomorrow that they want to control Bitcoin and they, purchase all of these huge mining rigs and spend that power, then yes, they would be able to.
Okay.
Yeah.
Great. There's a lot here.
Yeah, there's a lot.
We could go
Yeah.
on for a long time,
Yeah.
but that was wonderful.
Good.
Thanks very much.